9, which is single replacement reactions, and we're going to deal with a battery a little bit. So let's talk about single replacement reactions. Single replacement these are the general form. A plus bx makes ax plus b. So what's happening here is A replaces B, if A is more reactive than B. Right? I like to think of it like the game King of the Hill when we were kids. So when I was a kid, we'd play this game King of the Hill, and someone would climb up the hill and proclaim themselves king, and someone else could try to knock them off if they were bigger, meaner, and uglier than they were. So for example, here, B is king of the hill, X is the hill. A tries to knock B off. So what's happening is A knocks B off and B is by itself. So A knocks B off if A is more reactive. But if A is less than reactive than B, that means no reaction. So if there's no reaction, that means A is less reactive than B. Right? So for example, and in the lab you'll see this, I uploaded some videos for you or some photographs of some reactions. So for example, if we take this reaction, copper plus silver nitrate. All right, and what happens is when you do this reaction, you put a piece of copper in some silver nitrate, and what you'll see is that you'll see silver, silver metal plating on the copper. And so that tells us that you literally see silver showing up on the copper. So that tells us that copper is more reactive than silver. To come up with the products, it's a little tricky because you'd have to know charges and stuff, but in this case you would have copper nitrate, and copper forms a +2 here that you would deal with later, and you guys can balance the equation. Now, if we did it the other way, if we took Ag plus copper nitrate, we would get no reaction. And that's consistent because silver tries to knock copper off, can't do it because copper is more reactive. So from doing reactions of this type, which you'll have the data for activity 1, you can tell which metals are more reactive than others. Remember that, and so for example, copper is more reactive than silver, silver is less reactive, right? And you just look at all the stuff that we've done all semester about evidence for chemical reactions. So typically you'll see a solid formed on another solid, or a color change, or bubbles, or things like that, right? You can use this to develop what's called an activity series. Excuse me for the phone. Activity series where you list metals from most to least reactive. Right, so in this case you'd say copper is more reactive than silver, and then you could put a whole list together. right? So that's basically the first part. You're just looking for evidence of a reaction. Now that's the first part. And also one thing to remember is in an acid, we haven't really dealt with acid-base chemistry and we won't until later, but in an acid, where is this thing? The acids are H something X. In an acid, hydrogen acts like a metal. So for example, if you did magnesium plus HCl and you got a reaction, then you would say magnesium is more reactive than hydrogen. All right, so that takes care of activity 1. Let me erase the board here. In just a second. I apologize for my phone ringing, but I can't control that. Activity 2, again, you're not going to actually do it, but you're going to, so single replacement reactions are used in plating. So if you want to get something silver plated or stuff like that, it's a little bit trickier than just plopping things together, because to make a nice plating, you want the surfaces very clean, you want all the solutions very clean. But another thing that's interesting is this is how batteries work, and from the lecture you should know this. So in a battery, also use single replacement reactions. I'm going to abbreviate single replacement reactions. And again, the battery that you would have made is magnesium and copper sulfate. Now what happens in this reaction too is this would give you magnesium sulfate and copper. And what you'd actually see here is magnesium is becoming a magnesium ion. The sulfate just kind of sits there, doesn't really do anything. And the copper, which is a 2+ ion, becomes copper metal. The way it does this is this actually spits out 2 electrons, and then these electrons go here to the copper. So you're literally transferring electrons from the magnesium to the copper, a reaction like this. Now, if we just put these in the same container, the reaction would happen on the surface of the magnesium and you would plate out copper. But if we separate them, so I'm going to do a really bad drawing here. This is a beaker. We put a piece of magnesium in here. Let's have this be MgSO4. Then we have another beaker over here. And in here we put a piece of copper. It's supposed to be a U. And I have copper sulfate. And then we attach these with a wire. The electrons have to go through the wire to get there. Oops, I don't need that extra electron there. Just get rid of that. Right now, if we let this thing run for a minute, though, what would happen is that as the electrons moved here, this would become very positive and this would become negative. So typically what we have to have is we have to have a salt bridge, which is typically a tube just filled with ions. So typically you'd have something like, in this case, we might have potassium sulfate. And what happens is, as this reaction runs, the electrons go this way, the sulfate ions, this becomes positive, the sulfate ions will go this way. And as the electrons go this way, this becomes more negative, the potassium ions will go here. Right? Now, in the lab that you would have done, instead of having them separated, and this creates a voltage, in this case I think it's about 1.4. In the lab you were going to do, we're going to do it this way. So we have a big container, and this is full, this liquid here would be magnesium sulfate. It's a beaker. You have a piece of magnesium here. Mg. Right? And then here we'd have in a bag a piece of copper. And this bag would be full of copper sulfate. And we use what's called dialysis tubing, which is just very porous bag. And so the ions can flow. So the salt bridge is basically here. And then we attach these to a voltmeter like this. And the electrons would still go from the magnesium to the copper. This comes out to be about 1.4 volts. And there's a video of one of these where they use several of them. But that's the idea. In a battery, all you're doing is you're taking the reaction, and there's, of course, a much better picture of this in the lab manual. But in a battery, you're taking the reaction, and you're just separating them physically so that the electrons have to go through a wire to get there. Once electrons are going through a wire, right, then they can do all sorts of work on the way. They can turn on a light or so on. So that's what what this lab is about. Put up some pictures and some videos for you to actually look at the data. And it's unfortunate we weren't able to do this, but safety first. All right, I hope that explains this enough for you guys. And if not, as you know, I'm available on Zoom to help you. And have a good time working on it. Miss y'all. Bye.